So we start with the first paper of the session, and the speaker is Felipe Soares, and the paper is Collective Embedding for Neural Context-Aware Recommender Systems.
Good morning, everyone. So this work was together with my former supervisor, Peter Dolog, with Oliver University, and together with CNQ, and also some of the company is working on. Yes. So recommender systems have been doing a lot of progress in different aspects, recommendations, and there are a lot of things going on right now in diversity and fairness. And there are a lot of things going on also in the context of our recommendations, so also considering different dimensions as locations, as time, and companion of other people when users interact with other medias. But there is a focus also in the time of recommendations, where you consider the time as an important feature when recommending something to a user. And here's just an illustration where you have a user interacting with different medias. And then you have a recommend engine, and then this recommend engine is going to recommend some list of items for the user. What is important to note here is you can actually model the time in basically two different ways, like time dependent, where you have the sequence of items that have been using that have been interacted by the user as an important factor. Or you cannot, and then with that you can actually have the change that have been captured in there, the preference of the user. Or you can actually have the time aware, where you have the timestamps, the time slots that the user has been interacting through different times of the day with the vendors. But there are some challenges how to actually model or to embed time as a context from the user and also item perspective, and then recommend something in that. Then we actually propose to this model, the Latent Chapter model for recommended systems, where we actually where we have the 6 layers in there. We have the input layer, where we have the user and item ID, and then we also have the time that the user was interacting with the item, and also the time stamp where the item was interacted with. It's important to note here, the timestamp was actually modeled using the hours of the day, so 24 timestamp block in there. Then you have the embedding layer, embedding those user and item, and also the interactions with the time-based user embedding, and also the time-based item embedding. We have the interaction layer, where we actually map this interaction between the user, item, and also the time in there, using the outer product. Then we use the convolutional layer as an input the interaction, and then to capture the non-linear interactions in there. After that, we have the function layer, where we actually have the concatenation of the outputs of the convolution layers in there. And then we have the prediction layer, where we predict the score behind it. And then we have for the experimental settings to test if our model was actually working. We did test using the setting some hyperparameters, the ones that actually, during our tests, gave us better results. So the embedding size was 7 to 64, and then learning rate and batch size. We used different metrics, the NSG and the HMR metric to the ranking. And it was tested in 3 different datasets, the movie lens, IL, and Pinterest. It's also important to note here, like the movie lens is explicit feedback, so we actually have ratings in there. But in our case, we also wanted to model or to map it as in place, so actually the ratings was converted. If you have like any interaction in the item, money rating that will convert it to one to represent interactions in there. So then, as a result, we actually compare for top 10 and top 20 in their ranking list. And we had different methods. We had the contextual arithmetic factorization. We had the tensor factorization. But you see in the bottom, in our model, it performed better in the others. Do some different factors. Actually, for some of the methods, for example, the BPR, it doesn't we didn't consider the only item, the time in there. So actually, due to that, it was not giving the best personalization. The neurometric centralization, it used a loop perceptron, and then we actually, when we use the convolutional neural networks, we were able to get better results than them. The convolutional metric centralization method here, we didn't actually were able to use the time with them, so also influenced the results in the end. Also to evaluate the variation that we could have considering our hyperparameters. We have the regularization term lambda, where you have different variations, and when we set from 1, we actually start to converge quite well, and that variation didn't drop that much the performance. Also, the number of factors. We also, after setting to 32 and above that, we actually managed to converge more or less in the same way. So, we actually, time plays an important role in the recommendation process for us, because some of the methods that are not using time actually have a lower performance. CNNs are able to learn the nonlinear correlations among the user items and the time. And then due to this variation of the hyperparameters converging, actually we're able to use in the real world. We also like to explore other contextual features in our model. Also considering a lot of things going on in reviews, and it's also able to get a lot of features from there that is more precise or close to the user's preference. Also social relations from the users. And thank you very much.
Okay, time for questions. Any question? Okay.
Hi, thank you. I have a question about negative sampling. What did you use for it? What was your approach? And have you tried to add CNN to NIUMF as a third network and see the results, how it will perform? Thank you.
Sorry, can you repeat? Sorry.
Yes, so first question is about negative sampling.
Yes.
What was your approach there?
I actually didn't know like the negative sampling properly in there, so maybe this could be actually influenced in the result or the good performance you have.
Okay, and how much time do you take to train the network on the different sets?
It's around like 1 hour per training.
And have you tried to add CNN as a part of NILF, as a short network, and see the results there? Okay, thank you.
Okay. So we have time for another very quick question.
Okay, thank you, Doctor. For the encoding of the time step, would you please give us some more details? The encoding of the time step.
Yeah, I basically like encoded the interaction. So actually, it just counted if the user interacted with some kind of media in that specific hour. Then I counted 1. If it's not, 0. So there's a vector there.
For each hour, there will be something like 1 hot interaction.
Yes.
Okay, thank you.
Thank you. Let's thank the speaker again. Thank you very much.